If, on a certain evening about 66 million years ago, you had stood somewhere in North America and looked up at the sky, you would have soon made out what appeared to be a star. If you watched for an hour or two, the star would have seemed to grow in brightness, although it barely moved. That's because it was not a star but an asteroid, and it was headed directly for Earth at about 45,000 miles an hour. 60 hours later, the asteroid hit. The air in front was compressed and violently heated, and it blasted a hole through the atmosphere, generating a supersonic shockwave. The asteroid struck a shallow sea where the Yucatan Peninsula is today. In that moment, the Cretaceous period ended and the Paleogene period began. A few years ago, scientists at Los Alamos National Laboratory used what was then one of the world's most powerful computers, the so-called Q machine, to model the effects of the impact. The result was a slow-motion, second-by-second false-color video of the event. Within 2 minutes of slamming into Earth, the asteroid, which was at least 6 miles wide, had gouged a crater about 18 miles deep and lofted 25 trillion metric tons of debris into the atmosphere. Picture the splash of a pebble falling into pond water, but on a planetary scale. When Earth's crust rebounded, a peak higher than Mount Everest briefly rose up. The energy released was more than that of a billion Hiroshima bombs, but the blast looked nothing like a nuclear explosion, with its signature mushroom cloud. Instead, the initial blowout formed a rooster tail, a gigantic jet of molten material, which exited the atmosphere, some of it fanning out over North America. Much of the material was several times hotter than the surface of the Sun, and it set fire to everything within 1,000 miles. In addition, an inverted cone of liquefied, superheated rock rose, spread outward as countless red-hot blobs of glass, called tektites, and blanketed the Western Hemisphere. Some of the ejecta escaped Earth's gravitational pull and went into irregular orbits around the Sun. Over millions of years, bits of it found their way to other planets and moons in the Solar System. Mars was eventually strewn with the debris, just as pieces of Mars, knocked aloft by ancient asteroid impacts, had been found on Earth. A 2013 study in the journal Astrobiology estimated that tens of thousands of pounds of impact rubble may have landed on Titan, a moon of Saturn, and on Europa and Callisto, which orbit Jupiter, 3 satellites that scientists believe may have promising habitats for life. Mathematical models indicate that at least some of this vagabond debris still harbored living microbes. The asteroid may have sown life throughout the Solar System, even as it ravaged life on Earth. The asteroid was vaporized on impact. Its substance, mingling with vaporized Earth rock, formed a fiery plume, which reached halfway to the Moon before collapsing in a pillar of incandescent dust. Computer models suggest that the atmosphere within 1,500 miles of ground zero became red-hot from the debris storm, triggering gigantic forest fires. As the Earth rotated, the airborne material converged at the opposite side of the planet, where it fell and set fire to the entire Indian subcontinent. Measurements of the layer of ash and soot that eventually coated the Earth indicate that fires consumed about 70% of the world's forests. Meanwhile, giant tsunamis resulting from the impact churned across the Gulf of Mexico, tearing up coastlines, sometimes peeling up hundreds of feet of rock, pushing debris inland and then sucking it back out into deep water, leaving jumbled deposits that oilmen sometimes encounter in the course of deep-sea drilling. The damage had only begun. Scientists still debate many of the details, which are derived from the computer models, and from field studies of the debris layer, knowledge of extinction rates, fossils and microfossils, and many other clues. But the overall view is consistently grim. The dust and soot from the impact and the conflagrations prevented all sunlight from reaching the planet's surface for months. Photosynthesis all but stopped, killing most of the plant life, extinguishing the phytoplankton in the oceans, and causing the amount of oxygen in the atmosphere to plummet. After the fires died down, Earth plunged into a period of cold, perhaps even a deep freeze. Earth's 2 essential food chains, in the sea and on land, collapsed. About 75% of all species went extinct. More than 99.9999% of all living organisms on Earth died, and the carbon cycle came to a halt. Earth itself became toxic. When the asteroid struck, it vaporized layers of limestone, releasing into the atmosphere 1 trillion tons of carbon dioxide, 10 billion tons of methane, and 1 billion tons of carbon monoxide. All 3 are powerful greenhouse gases. The impact also vaporized anhydrite rock, which blasted 10 trillion tons of sulfur compounds aloft. The sulfur combined with water to form sulfuric acid, which then fell as an acid rain that may have been potent enough to strip the leaves from any surviving plants and to leach the nutrients from the soil. Today, the layer of debris, ash, and soot deposited by the asteroid strike is preserved in the Earth's sediment as a stripe of black about the thickness of a notebook. This is called the KT boundary, because it marks the dividing line between the Cretaceous period and the Tertiary period. The Tertiary has been redefined as the Paleogene, but the term, KT, persists. Mysteries abound above and below the KT layer. In the late Cretaceous, widespread volcanoes spewed vast quantities of gas and dust into the atmosphere, and the air contained far higher levels of carbon dioxide than the air that we breathe now. The climate was tropical, and the planet was perhaps entirely free of ice. Yet scientists know very little about the animals and plants that were living at the time, and as a result they have been searching for fossil deposits as close to the KT boundary as possible. One of the central mysteries of paleontology is the so-called 3-meter problem. In a century and a half of assiduous searching, almost no dinosaur remains have been found in the layers 3 meters, or about 9 feet, below the KT boundary, a depth representing many thousands of years. Consequently, numerous paleontologists have argued that the dinosaurs were on the way to extinction long before the asteroid struck, owing perhaps to the volcanic eruptions and climate change. Other scientists have countered that the 3-meter problem merely reflects how hard it is to find fossils. Sooner or later, they've contended, a scientist will discover dinosaurs much closer to the moment of destruction.